Quiz number 2. Here are the questions. Why does going 100 feet underwater have a greater effect on your ears than going down a 100-foot hill? The water is more dense. Remember, the pressure changes by changing pressure. Tell me what these symbols mean. What is the first symbol's name and what does it mean? Rho is the first one's name, and what does it mean? Density. The second one, she says gravity. That's the acceleration of the Earth's gravity. And then H is height, or in this case, it's the depth. We still use H, but it's the depth you've gone down. So that was number 1. Number 2, what is the definition of pressure? Force per area. Mass per time doesn't have some simple definition. Mass per unit volume, what's that one? That's density. And force per unit mass, if it said net force per unit mass, it'd be the acceleration. Right, because Newton's second law says acceleration is force. Okay, next one. When a skydiver jumps from an airplane, what is happening to energy? Now, this anthermal was because while we don't talk about it, we know that we lose some energy to air resistance. And so that's what the anthermal is. But I had in parentheses anthermal in case somebody wants to get all technical. Wait, it goes somewhere else too. So the hot tip is it's got to be C or D. Energy is energy being converted from potential to kinetic or from kinetic to potential? Potential to kinetic. Potential energy is the energy it has because of its position or configuration, in this case gravitational potential energy. And kinetic is the energy it has because it's moving. And finally, the last one, which a student asked this because I made a big deal about 2 of these units are technically the same, but only one is used for torque. So which one is used for torque? PA is pressure. That's a Pascal, so that's used for pressure. Newton meters is indeed the torque. At least a few good informed guesses, right? It wasn't in blind space. Which one of these is the same as a Newton meter? Yes, but that's used for energy only. It's a Newton meter, but it's only used for energy. And then what is W? It's confusing. W as a symbol is work. W as a unit is watts for the unit of power. So you have to pay attention to, is it a symbol or is it a unit? But since that was not the answer here, it wasn't important to distinguish. It does say unit here, so it had to be power. Okay, now to the regular part of the lecture. Uh-oh. Yeah, you're not doing quantum mechanics. Probably knew that though, didn't you? Okay, we've been talking about fluids, and we're going to finish talking about fluids today. So buoyancy is where I left off last class period. Buoyancy is the effect of being buoyed up or lifted up because of a fluid around you. And Archimedes' principle relates tightly to this. So remember, I ended last class period talking about Archimedes and the crown, and he realized that when he went in the bathtub, why the water level went up, and that the volume that he displaced was equal to his volume. That is, if you were to take me and shove me under the water, the amount of water that would be pushed out would be equal to the volume of me. So if you shove me underwater and you shove Mariah underwater, I'm going to push a lot more water out of the way than Mariah does because I'm bigger. I take up more space. Now, in doing this, he started thinking about exactly what makes something be pushed up, why something float. And with higher pressure on the bottom, pressure is force per area, you're going to have a higher force on the bottom. And so he did a calculation and determined that the weight of water displaced equals the buoyant force. That is, if you get in the bath or you get in a swimming pool, and if you float, then you know the downward force on you is the force of gravity. And if you float, that means you're not accelerating up or down, you're in equilibrium. We just talked about this idea. So the upward force on you has to equal the downward force due to gravity. And when you're in the water, what's making the upward force? Okay, it's the buoyant force. It's the force of the water pressure pushing in on you. And because the water pressure is greater as you go down, it's pushing up harder on your feet than it is, on your armpits if you're vertical. If you're horizontal, it's changing. But it turns out it doesn't matter what position you are, the total force you're going to get from that water is going to be an upward force that's equal in weight to the volume of the weight of the water you displace. So if your density is less than the density of water, that means that your total body's displacement will be bigger than the displacement of water weighing the same. Now let's back that up just a little bit and remember what density is. Density is equal to mass divided by volume. So we have the mass of Richard is equal to the density of Richard times the volume of Richard, right? And if you put me in water, I'm going to, if I float, the volume displaced has to be less than the volume of Richard. That is, part of me has to be out of the water. So I didn't displace water equal in volume to my entire volume because part of me is not in water. So, if I'm in the water and my head's sticking out, then the volume I displaced is equal to the volume minus the volume of my head. So the volume displaced has to be less than the volume of Richard if I'm floating. But according to Archimedes' principle, the force buoyant is the mass displaced times gravity. Well, the mass displaced is going to be, using this equation, density is mass over volume, then the mass displaced is the density of the water times the volume displaced times G. Yes.
So how does that all relate at all? Like, what are we looking for? Because how is the mass displaced times gravity equal to density of the weight volume displacement?
Okay. Let me go 2 more steps here, and we'll get to that. So that's the force buoyant. But we said that if I float, what's the relationship between, what's my net force if I float? Zero, because I'm not accelerating up or accelerating down, just staying constant. And that's going to be the buoyant force pushing up minus the force of gravity pushing down. So from what I just did, density of water, volume displaced, times G, minus my mass, right? Mass of Richard times G for my weight. That's supposed to be an R, which is density of water, volume displaced times G minus density of Richard, volume of Richard, G. I replaced mass with density times volume for me as well. Now, since this is equal to 0, I can cancel out the g's, and we see when I float, density of Richard times volume of Richard has to be equal to density of water times the volume displaced. Yeah, that's F subscript G. Is that what you're asking? Is it clear now? Okay. So now I get to what she was asking. What does this mean?
How would we, let's just say we're doing that on a test or whatever. You said this is equal to that. How would we know that? Like, because it just doesn't make sense.
Okay, there's a lot of things I said in this process. So how would we know which piece? Let me go to the beginning of how we know things. This is a definition. You'll be given that equation on the test, right? And so this calculation here, of course, that's just taking that equation, solving for mass of Richard, which is what I put in right there. Mass of Richard was volume of Richard times density of Richard. Then the next statement, if I float.
Well, M is equal to, so you just replaced it.
Well,
since M is equal to that, you just, for the M, you put.
I put density times volume, yes.
Okay.
And so I also did that in the force of buoyancy, but let me go through continuing. If I float, there's nothing you would be given on that. You would just have to say, wait, if you float, that means part of you is not in the water. So part of you is not pushing the water out of the way. Hence, the water you push out of the way is smaller than your total volume. So that's a logical sequence. That's not something that you would be given or have an equation for. It's something you would recognize if I float. Then I had Newton's second law over here to say, now, how does the buoyant force pushing me up relate to the force of gravity down if I'm floating? And then I just substituted the buoyant force, which we already calculated, and the force of gravity, and then I solve for the ratio of densities. And so this is where it's important, the outcome, since the volume displaced is less than the volume of Richard, and if I'm floating, the density of Richard over the density of water is equal to that ratio of volume displaced, then the density of Richard has to be less than the density of water for Richard to float. So the outcome of this is, you probably already knew, rocks sink and styrofoam floats. And rocks, a rock that's this size is pretty heavy, where styrofoam the same size is very light. That's what density is all about. And so you have these ideas in your head, but now we have a math relationship that we can actually follow through that says, yes, the less dense things float, more dense things sink. So you have a homework question about iron floating on mercury. What does that tell you if iron floats on mercury? Liquid mercury, of course. Yeah, it tells you that the iron is less dense than the mercury. But why does iron then sink when you put it in water? It's more dense than water. Because water is, mercury is 13.6 times more dense than the water is. So all of this is to go through the example we just did. So now a question to make sure that you're following along on which of these blocks. So we have 1 kilogram blocks of lead, aluminum, and uranium. And notice it tells us the relative densities. Aluminum is low density, uranium is high density, and lead is intermediate, believe it or not. So if you have 1 kilogram of each, which has the greatest buoyant force? Or are they all the same? Or all they? Okay, I'm not going to speak English anymore. Okay. Everyone answered. Don't know. 2 people answered again because of the failure of the program.
Put it again.
No. 2 people answered a second time because the clicker program's not working right. Okay. At the very end, Leslie changed her answer so that she would be the only one with the right answer.
I thought about it for a second.
The correct answer was aluminum. And you're probably saying, why? Right, 3 people, a plurality, well, it's not even a plurality because it was a tie for the 3 people said that they would all have the same. I can see the reasoning somebody would come with that because they have the same mass. You think, well, it should have the same buoyant force. But the buoyant force is not based on mass. What was it based on? According to Archimedes, the buoyant force is equal to the weight of the displaced fluid, which is proportional then to the volume of the object. So since they have different densities, they're not going to have the same volumes. So they're going to have different buoyancies or different buoyant forces because they have different volumes. And so then going back to Archimedes again, the one that displaces the most water is going to have the biggest buoyant force because the buoyant force is the weight of the volume displaced. So the one that displaces the most, the one with the biggest volume, is going to have the biggest buoyant force. So of the densities, density is mass over volume. Let's just write this down to make sure everyone's clear. Density is mass over volume. Therefore, volume, ... means therefore. The volume is equal to the mass divided by the density. So that means if you have a high density, you're dividing by a big number and you have a low volume. If you have a low density, you're dividing by a small number, you can have a high volume. And which volume is going to have the biggest buoyant force? Bigger or smaller? Bigger. Yeah, because the buoyant force is the weight of the displaced fluid. So the bigger the volume, the more fluid it displaces, the more the buoyant force. So the one with the biggest density is going to have the smallest volume and thus the smallest buoyant force. The one with the smallest density is going to have the biggest volume and thus the biggest buoyant force. So the aluminum, and we could go back to things you know, and if you put it in terms of the things you know, you would have answered right. If you would have said, if I take 2 blocks, one is a low density material like styrofoam, and one's a high density material like lead. And if those blocks are the same exact mass, what's going to happen? How the size is going to compare? Which one's bigger? If I have a 1 kilogram block of styrofoam versus 1 kilogram block of lead, which one's bigger? No, kilogram is mass, but lead is very dense, so it doesn't take much lead to reach 1 kilogram. But the styrofoam is going to be a huge chunk of styrofoam to be 1 kilogram. But they weigh the same because they're both 1 kilogram. Mg is the same for both. If I put them in water, only one of them floats. The styrofoam floats, the lead sinks. So they have the same downward force. Clearly, the upward force in the styrofoam was bigger for it to float. The lead didn't have an upward force big enough to make it float, and it sank. So you had to have a bigger upward force on the styrofoam because of its low density. Okay, let's go past this and get to pressure in gas. What causes the pressure? Pressure is a force over area. And when I step on your finger, it's really easy to say, oh, well, you know, your foot's pushing on my finger. It's a force being distributed over my finger. That makes sense. If I'm in water, what's happening to make me feel water pressure? It's not a solid now, it's a liquid. What makes me feel the water pressure? Or likewise in air, what makes me feel the air pressure? You have an answer?
Can you ask the question again?
Well, what makes me feel pressure from water or air?
How do you feel it?
Yeah, how is it possible I can feel it? What interaction is making me so I can feel it?
What was it like?
Okay, when you get down to it, I'm just going to take it on faith that everybody's really fuzzy on the idea. When you get down to it, both air and water have lots and lots of molecules that are moving around. And because they're moving around, they'll fill spaces. So if I pour water in a dish, it will fill the dish up to a certain level and fill out whatever shape is available to it up to its level. Gas, it'll fill any shape. In both cases, they fill things because the molecules are moving all around really quickly. And so whether you're in water or air, you're feeling the molecules bouncing off your skin. They're colliding with you. And so that's what makes us feel the pressures, the collisions, accumulated collisions between billions upon billions of molecules with our skin. So the molecules are moving around. And wouldn't it be nice if we could tell how fast they were moving? Wouldn't that be cool? Of course it would. And in physics, of course, we're all about cool. Of course we are. And so we measure the temperature. Temperature measures the average kinetic energy of the molecules. Now, when I say this, it measures the average kinetic energy. There's a little bit of fuzziness on this. It depends on, if it's a gas. If it's a gas that has one molecule or one atom per molecule or 3 atoms per molecule, it's going to be a different relationship between the average kinetic energy and the temperature. But the temperature is proportional to the average kinetic energy. So if you raise the average kinetic energy, you're going to raise the temperature. And the same is true for a liquid. The temperature is telling us about the average kinetic energy of the molecules. So when something is a higher temperature, if it's hotter, that means the molecules are moving faster. And so you absorb more energy when those molecules bounce off of you. And hence you feel a difference. So temperature has to do with the average kinetic energy of the molecules. So if you take a gas and you compress it, you make it so it has less volume, you are actually going to cause the pressure to go up and the temperature to go up. So if you probably pumped up gas in air in a bicycle tire, and when you pump that, the pump gets warm. It gets warm because when you compress the air, it got hotter. You made the molecules go faster because you put energy into them. If you double the density of the air, that is, if you cut the volume in half, then the pressure goes up and you're probably going to have temperature go up. We have a couple different laws that come together to give us the ideal gas law. I'm not going to go through each law individually. I'm just going to put them together. I'm not giving you this question as a clicker question, but it's a good one. 2 people are drinking soda using straws. Do they suck the soda up? Could they drink soda on the moon this way? Have you ever thought about how you can drink out of a straw? I'm not asking this as a clicker question, so you don't have to worry about answering. But have you thought about how you drink with a straw, or are you just like, since you're a kid, you've been drinking with a straw? It's got to be one of the two. Yes or no? You thought about what's going on when you drink with a straw? No. You just do it. Well, it has to do with pressure. Pressure is force over area. And pressure can never be negative. It's always positive. You can get down to zero pressure, which we call a vacuum. So normally you have atmospheric pressure. Atmospheric pressure is on everything here. When you're drinking through a straw, what do? You pull air into your mouth, right? And when you pull air into your mouth, that removes some air in your mouth. It lowers the pressure in your mouth. Now, the air in your mouth is still above vacuum. There's still air bouncing around in there. But it's lower pressure than the atmospheric pressure, which means that the air inside your mouth is pushing down on the water, if you're drinking water through the straw. But it's not pushing down with as much force per area, not as much pressure, as the air pressure is pushing it up the straw. And so when you're drinking with a straw, you lower the pressure on top, and atmospheric pressure pushes the fluid into you. So you really can't suck anything with a straw. All you can do is lower the pressure, and then atmospheric pressure pushes it into you. So if you were on the moon that has no air pressure, what would happen if you tried to drink with a straw? It wouldn't work because you don't have the air pressure to push it into you. Yeah.
So why is it like when you start with the straw and there's nothing there, it like suctions?
It's lower pressure than the air pressure.
So you're doing all that work, but you're not doing any work.
You've pulled out some air, so the pressure inside is less than you normally have. And so, of course, that means air is trying to push in. And it's not pushing in as much there. If you kept going down, you get to zero pressure, and it'd be, like we talked about, if you were having zero pressure, your eyes wouldn't come out of your body, but yeah.
So what about when, at least me, I would do this when I was a little girl. I would grab the cup and then I would put it to my mouth and I would suck and it would get like stuck to my mouth.
Yes, I did that too. I did that too. I had a big purple ring.
Yeah.
And so what you're doing is you're lowering the air pressure inside the cup. Atmospheric pressure is pushing the cup on you. You're not pushing it away as hard. And so it's being held on by atmospheric pressure. Just like a suction cup. So the correct answer here was, could you drink, do you suck the soda up? No, you can never suck. Could you do it on the moon? No. So that was the correct answer. Now, Pascal's principle is something that I implicitly assumed in the previous discussion. Pascal said that if I have a constrained fluid, a fluid that doesn't have gaps or anything in it, doesn't have air bubbles, if I increase the pressure one place, the pressure everywhere in the fluid is going to increase by the same amount. So, for instance, if I have a column of water, the pressure on the bottom, the pressure on the top is atmospheric pressure because atmosphere is pressing down. Pressure on the bottom is atmospheric pressure plus rho GH, where I use the density of water and the height of my column. If I push down, if I use a plunger to push down harder, the pressure everywhere is going to go up by that amount. That's really important for things like a hydraulic lift. You take your car, well, actually, here's a practical example. A couple days ago, I was at the little recycle center over there, right over there, and there was a trash truck picking up a full recycle bin. And it's got these big hydraulic rams. Have you seen those somewhere? Somewhere, anywhere? Yes?
What are you talking about?
Like the ones that can press it?
This was just the big rams that raise and lower. So you see, they look very shiny, metallic because they're stainless steel. And they use them to raise and lower things like a dump truck or a car lift. Those are examples of using Pascal's principle. What you do is you have something like this, except for you make the sides different areas. And since pressure, see, they're different areas. Since pressure is force over area, then you can have on the small area, you can have a relatively small force to create pressure. On the big area, because you have a large pressure, you'll have a big force. So in this example here, the pressure is the same on both sides. That means the force over area is the same. On the left-hand side, we have 10 kilograms. What's the force down due to 10 kilograms?
Wait, what? What did you guys say?
If I have 10 kilograms, what does it weigh?
Yeah, 10 kilograms. Is it?
That's its mass, not what it weighs.
Oh, what it weighs. Okay.
You have to multiply it by 9.
Yes, I have to multiply it by 9.8. So that would be 98 newtons on that side. The other side has 50 times the area. So the force that it can push up is going to be, since force is pressure times area, it'll be my original pressure of 98 newtons divided by area, multiplied by my new area, 50 area. So it can lift 50 times the weight. And that's 50 times the mass, hence the 500 kilograms. And so in something like lifting a car, you take your car to the shop and they lift it up so that they can work underneath it. They use some relatively low pressure oil that's pumped with a little tiny opening like this. So while it has a very high pressure, the force that you need to put on the oil is pretty small. Right, small force, big area, or small force, small area can make a big pressure. And then it goes into a hydraulic ram with a really big area so that it can have big area, the same pressure, make a much bigger force. So the whole idea of a hydraulic ram is pressure 1 equals pressure 2, force 1 over area 1 equals force 2 over area 2. Force 2 is what you want to lift, is equal to force 1 times area 2 over area 1. So if you have area 2 is 50 times bigger than area 1, then force 2 can be 50 times bigger than force 1. So that's another kind of simple machine, something that allows us to do work with less force. Still have to have the same total work. So with something like the hydraulic ram, to lift a 500, well, we can just look at this picture. If I lower this by 1 foot, because the area over here is so large, the volume here, volume is area times height. Because it's such a big area, that same volume is going to be consumed with a very small increase in height. So you have to have a lot of oil that you can pump with your hydraulic system, because you have to move a whole lot of oil at lower pressure to have the really big motion upward. And so, yes, this is showing exactly what I just wrote. Pressure 1 is pressure 2, force 1 over area 1 is force 2 over area 2. And there's a picture showing how you use the lift at the garage. It's using the air compressor to compress our fluid that we use in the reservoir. So now when you go to the garage and you see that lift, you can say, oh yeah, I totally understand how that's going, right? Right. Yeah. Maybe. Okay, now we're going to talk about flowing fluids. Fluids flowing is kind of fun. And the first thing we're going to do that's fun is we're going to talk about Bernoulli's relation. Bernoulli, discovered by Daniel Bernoulli in like the 15th century, states that when the airspeed increases, the air pressure drops. So what that means is if I have my blow dryer here, which I disconnected the heating element on, so I don't have to worry about it getting hot. If I turn this thing on, where the air is blowing, it's going to have a lower pressure. Now, how could I visualize that lower pressure? Well, the standard way is to put this over the edge and blow air over the top. If the pressure is lower on the top than the bottom, what's going to happen? Okay, Danny is right. She's the only one I've seen respond, so that's why I just said Danny's right. Okay, tell them what you said, what you showed with your hand, Danny. Okay, it'll pull it up because, well, does it really pull it up? No, the air underneath will push it up. So let's check. And it did. When I had air blowing over the top, it came up. So that's what Bernoulli's principle says is the air flows over, it's going to lower the pressure. Now this leads to, well, some unfortunate things. Let's say you have a really high wind condition, like a tornado. Tornadoes have really fast wind speeds, right? Well, when you have a really fast wind speed, here's a box house. I guess we're homeless, we're living in a box. Wind is blowing over the top of this house. If the wind's blowing over the top of the house, what's happening to the pressure pushing down the top of the house? It's decreasing. But inside the house, you have still air. So you have atmospheric pressure inside the house and a lower pressure on top. What's that going to do? You have air pushing down the top, not very hard, air pushing up from the bottom really hard. Once again, Danny gave the right hand signal. It's going to try to peel the roof off. And so that's a big concern. When you have high winds, you know, houses are, usually you expect that the roof is going to be pushed down, you know, its weight and whatnot, that it's going to stay there. But you lower the pressure on the top and that roof can come up. And you don't have, you know, support beams holding the roof down. You do have nails and whatnot, but it's not nearly as strong. And so when you have those heavy winds, you can have the roof lifted off the house, which, you know, causes damage. That's a negative effect of Bernoulli. There's positive effects too. And I'm sure I have slides coming up of this, but given the time, I just want to get to my pictures and do my fun thing. What do you suppose that's supposed to be? It's actually not a bad picture, I think. It's supposed to be the wing of an airplane. Really? This is the side view of the wing of an airplane. Now, some things that are important. What direction would the airplane be traveling with a wing shaped like that? It travels like this. I'm going to put airplane. There's a reason it has that blunt edge. It has the blunt edge so the air can streamline around it. So you have air relative to the wing. The air is going like this and like this. And the air splits nice and smooth because of that blunt edge. If the wing had a sharp edge, it would just cut the air. And it wouldn't work as well. We want it to split smoothly. Depending on your angle and whatnot, not have a problem. The bottom is flat. So the speed of the air relative to the bottom is the distance of the bottom divided by the time it takes for the airplane to move forward, the length equal to the distance of, or the width of the wing. The top, because of the curvature, the top is longer distance. But of course, the airplane's moving at the same speed, regardless of if you're looking at the top or the bottom. So the air molecules going over the top have to actually travel at a faster speed than the ones on the bottom because they have a larger distance to travel. But according to Bernoulli, if you have a larger distance on the top than on the bottom, what does that mean about the pressures? The speed on top is faster than speed on bottom. According to Bernoulli, that affects the pressure. How's the pressure going to compare between top and bottom? It's going to be lower on top because of the higher wind speed. So the pressure top is lower than pressure at the bottom. Now, if we want to calculate how much downward force the air is putting on the wing, we take what we call the cross-sectional area. We just take the area that the shadow has, which would be the same looking at the top or the bottom, and multiply by the pressure. So you have the same area, lower pressure on top means a lower force due to air on top than you have on bottom. If you have a bigger upward force than downward force, that's going to tend to lift it, right? Now you have the force of gravity that's also downward, and so airplane travels smoothly with its gravitational force being balanced by the net upward force due to the wind speed difference. Now you might say, well, what about the buoyancy of the airplane? It does have buoyancy, a very, very tiny buoyancy because the density of air is small, hence the pressure change due to elevation is very small. Likewise, there's a buoyancy on me, a very tiny buoyancy. And so the big thing that's going on, what's causing the lift for the airplane, come on, move. The lift is the difference in the force of the air on the bottom and the top. That's caused because the wind is going faster over the top of the wing than the bottom. Now, I just have to go to my next demonstration because we're out of time, and we're not going to have any more time to talk about fluids after today. I just love this demonstration. There's many demonstrations you can do. You might have seen this. Okay. This is not what I love. What's happening here? What was happening? Okay, I had air molecules that had an upward momentum. They hit the ball, and they bounced off, transferring momentum. And the change in momentum or change in time is force. And so the upward force due to the air was equal to the downward force due to gravity, and it was just staying floating in space. Okay, so here's what I love. What happened there? Okay, it levitated even though the air was not blowing straight up on it. I had the air blowing like this, and I had the ball levitating. How in the world does that happen? Give me what you think. What do you think was going on? Well, because we're out of time, I'll have to tell you. As you get it sideways, it starts to sink down in the airstream because of gravity. And so you have the air is flowing mostly over the top and not under the bottom. So the air over the top has a higher speed than the air under the bottom. Of course, if it has a higher speed, what does that mean about the pressure? It's a lower pressure on the top. So it's being pushed up from below more than it's being pushed down from above, and that's what was holding it up, which I think is totally cool. Okay, I'll see y'all in lab 2.
Can you just go back to the formula, the airplane?
Oh.
Yeah. That part.
Okay. So I'll see you for lab tomorrow.